Welcome to today's paper reading. Today's paper is titled ReFT, Representation Fine-Tuning for Language Models. This paper, titled ReFT, Representation Fine-Tuning for Language Models, is authored by Zhengxuan Wu and colleagues from Stanford University and AI2R Group. It is currently under review as a preprint. The abstract introduces the concept of parameter-efficient fine-tuning, PEFT, which aims to adapt large neural models by updating a small number of weights. However, previous interpretability work indicates that representations encode rich semantic information, suggesting that editing these representations could be a more powerful approach. To explore this, the authors develop a family of representation fine-tuning (ReFT) methods. These methods operate on a frozen base model and learn task-specific interventions on hidden representations. A key method in this family is low-rank Linear Subspace ReFT, LoReFT, which is identified as a drop-in replacement for existing PEFTs and offers significantly higher parameter efficiency. The ReFT methods are evaluated across various tasks, demonstrating a superior balance of efficiency and performance compared to state-of-the-art PEFTs. The authors also release a public training library for ReFT. Pre-trained language models are often fine-tuned to adapt to new domains or tasks, allowing a single base model to be adapted to various tasks with only small amounts of in-domain data. However, fine-tuning large language models is costly. Parameter-efficient fine-tuning methods aim to address these high costs by updating only a small number of weights, thereby reducing memory usage and training time. These methods achieve performance similar to full fine-tuning in many settings. In contrast, representation fine-tuning modifies model representations rather than weights, inspired by recent work in language model interpretability. This approach can be seen as a generalization of previous representation editing work, suggesting it might be a more powerful alternative to weight updates. Figure 1 illustrates the comparison of parameter count versus performance for LoReFT and other parameter-efficient fine-tuning (PEFT) methods across 4 benchmarks. The benchmarks include Llama, Llama 2, Llama 3, and Roberta models. Despite training significantly fewer parameters compared to existing PEFTs, LoReFT demonstrates competitive or even state-of-the-art performance on all tasks. The effectiveness of LoReFT is particularly evident in the largest models evaluated. Note that FT represents full parameter fine-tuning, which is not considered a PEFT or ReFT method. Further results and details can be found in section 4 of the paper. The authors classify parameter-efficient fine-tuning methods (PEFTs) into 3 categories. Adapter-based methods train additional modules on top of a frozen pre-trained model. Series adapters insert components between language model (LM), attention or multi-layer perceptron (MLP) layers, while parallel adapters add modules alongside existing components. These methods add new components that cannot be easily folded into existing model weights, imposing an additional burden at inference time. Low-rank methods like LoRa and Dora use low-rank matrices to approximate additive weight updates during training, requiring no additional overhead during inference. These are considered the strongest PEFTs currently. Prompt-based methods add randomly initialize soft tokens to the input and train their embeddings while keeping the LM weights frozen. These methods are often far from optimal compared to other PEFTs and come at the cost of significant inference overhead. The ReFT family of methods is motivated by the need for intervention-based model interpretability. This approach uses the causal abstraction framework and distributed interchange interventions (D2) to establish the causal role of representations. One key method within this family is low-rank Linear Subspace ReFT, LoReFT, which modifies representations in a low-dimensional subspace to steer model predictions. The ReFT family generalizes these intervention functions, defining a set of non-overlapping interventions with independent parameters for each function. This framework allows for a variety of inference time interventions, enhancing model control and interpretability. Figure 2 illustrates the concept of ReFT, representation fine-tuning. On the left, it shows an intervention where the intervention function phi is applied to hidden representations at specific positions P in layer L. On the right, it details the intervention function used in LoReFT, which calculates an edit vector that modifies the representation only within the linear subspace defined by the rows of R. The example provided demonstrates how a rank 2 LoReFT operates on three-dimensional hidden representations, highlighting the specific modifications made within this subspace. The experiments conducted by the authors evaluate their ReFTs against existing PEFTs across 4 diverse NLP benchmarks, encompassing more than 20 datasets. These benchmarks include both masked and autoregressive language models, ranging from RoBRT-based to Llama models. The comparisons are made against several existing PEFTs, with a focus on both performance and parameter efficiency. Hyperparameter tuning is crucial in these experiments, involving decisions on the number of prefix and suffix positions to intervene on, the layers to apply these interventions, and whether to tie intervention parameters across different positions in the same layer. Table 1 presents the accuracy comparison of Llama 17B/13B, Llama 27B, and Llama 38B models against existing parameter-efficient fine-tuning (PEFT) methods on 8 common-sense reasoning datasets. The datasets include BoolQ, Pika, Sika, HelloSwag, Winogrande, ArcE, ArcC, and OBQA. The performance results of baseline methods are taken from Liu et al. 2024 C, and the results for our methods are averaged over 3 runs with distinct random seeds. The parameter efficiency % for our methods is calculated by dividing the number of trainable parameters by the number of parameters of the base language model. Table 2 presents an accuracy comparison of Llama 1 models with 7B and 13B parameters against various parameter-efficient fine-tuning (PEFT) methods on 4 arithmetic reasoning datasets: Aqua, GSM8K, MAWPS, and SVAMP. The table highlights the performance of each method in terms of accuracy, with specific figures provided for each dataset. Notably, DReFT and LoReFT, the methods under study, are compared against baseline methods, showing their relative strengths and weaknesses in handling arithmetic reasoning tasks. The results indicate that while DReFT and LoReFT do not outperform all other methods, they still demonstrate competitive performance, especially with the larger 13B model. This suggests that the effectiveness of these methods may scale with model size, although further analysis is needed to confirm this trend across different types of reasoning tasks. Table 3 presents the evaluation results of instruction-tuned Llama 27B using AlpacaEval version 1.0. The table highlights that Llama 27B, when fine-tuned with LoReFT, achieves a win rate that is within 1% of GPT 3.5 Turbo 1106, outperforming all other reported fine-tuning methods. Notably, even with half the parameters or using only 1K training examples, LoReFT maintains its superiority over other methods, demonstrating its effectiveness in long-form text generation. DReFT, while slightly less effective than LoReFT, remains highly competitive. Table 4 presents an accuracy comparison between RoBRT-base and RoBRT large models against various existing parameter-efficient fine-tuning (PEFT) methods on the GLUE benchmark. The table highlights the performance metrics across different tasks such as MNLI, SST2, MRPC, COLA, QNLI, QQP, RTE, and SDSB. It showcases the effectiveness of LoReFT and DReFT in relation to other PEFT methods, emphasizing their competitive accuracy scores on the GLUE tasks. The current study has primarily focused on the LLaMA family of models due to resource constraints. Future research aims to extend the exploration of ReFT's effectiveness to other model families and vision language models. The capabilities of ReFT have not been fully explored due to the extensive hyperparameter search space, prompting interest in automating this process. Initial explorations of language model personalization with ReFT in a few-shot setting are provided in the appendix. The precise mechanisms by which ReFT operates require deeper investigation, particularly in understanding how it creates or modifies causal pathways within models. Future research should explore more structured ReFTs to modify complex causal pathways in language models. In this study, the authors propose LoReFT as a robust alternative to existing parameter-efficient fine-tuning methods (PEFTs). They also introduce DReFT, which balances performance with increased efficiency. LoReFT demonstrates significant efficiency improvements, being 15 to 65 times more efficient than LoRa, and sets new state-of-the-art performance benchmarks in common-sense reasoning and instruction-following tasks. Additionally, the authors present ReFT as a comprehensive framework for fine-tuning that enhances parameter efficiency and interpretability. The authors acknowledge the contributions of Zhengxuan in designing memorization tests and the broader team for their discussions and feedback on the project and manuscript. Thank you for watching.